Hi, I'm Yeshwanth, and I'm going to be talking about our work on outlier robust PCA. And this is joint work with Pratik and Praneeth at Microsoft Research. So let's talk about PCA. You're given a data matrix X star, where the columns represent the data points. So there are n columns, x1 till xn, and each of them are in d dimensions. And you want to find the rank R subspace which best approximates this data matrix X star. And formally, you try to find the subspace which minimizes that objective function. So one of the reasons that PCA is so attractive is because it can be solved very efficiently in order NDR time. But one fundamental drawback is that it's extremely brittle to the presence of outliers. So here is an illustration in 2 dimensions. The blue points are your true data points. And if you did not have any outliers, PCA would just give you this principal subspace. But let's see what happens if you add some outliers to the data set. So you've added these red points right here. And now you see that your estimated principal subspace is completely different from what you would obtain if you did not have any outliers. So this motivates the problem of outlier robust PCA. In this setting, you're given a matrix M star, which is the sum of your true data matrix X star plus a matrix of outliers C star. And C star has limited column support. And we work in the fully adaptive setting. So an adversary can look at your entire data matrix X star and decide exactly which columns he wants to corrupt. So in this example, in the picture here, the last gamma n columns are outliers. But in reality, you don't know where these outliers are. And the problem with the existing solutions to this outlier robust PCA problem are that they are computationally very heavy and they have weak recovery guarantees. So what are our contributions? We propose an algorithm TORP, which is really simple. It's based on really simple and intuitive operations like computing the SVD and hard thresholding. We achieve nearly the same runtime as vanilla PCA, and we also have strong recovery guarantees. So before we describe our algorithm, let's see how an adversary can probably try to trick you into figuring out wrong directions. So like some of these outliers are going to be pretty blatant. So these outliers are very far from the principal subspace and they can completely change your estimated principal component. So here you see that you estimate U, but it's mostly because of a few small outliers that are in the top left corner of the picture. So these outliers are really easy to detect. All you have to do is project your data points onto U. And now we can move on to the second type of outliers. These outliers are much closer to the principal subspace, but they are still far enough that they can perturb your estimate. And the earlier strategy of projecting your data points onto your estimated subspace U doesn't work anymore. But you can still detect these outliers by projecting onto the orthogonal subspace of U, U-perp, which is essentially computing the residual. And now you see that in general, outliers tend to have larger residuals than the inliers. And now we can describe our algorithm TORP. At every stage, we maintain an estimate of points that we believe to be the outliers. In each iteration, we compute the SVD of the assumed inlier points. We compute the contribution of each point to each principal direction. And we also compute the residual of each point with respect to the estimated subspace. And we take a union of the top alpha n residuals and the top alpha n contributors, and that forms our outlier estimate for the next iteration. And at the conclusion of the algorithm, we return the top R left singular vectors of, this should be M bar C. So let's see what kind of theoretical guarantees we have. So let's assume a scenario where the inliers belong exactly to a low dimensional subspace. So we have X star is equals to L star, a low rank matrix. So in this case, we achieve exact recovery of the principal subspace. So we get epsilon error in time order NDR log 1 over epsilon. But we require the fraction of outliers to be less than order 1 over R. But this is necessary if you want an exact recovery result. And we also require that each principal component is sufficiently spread out. Because if this is not true, then you don't know that a component that you estimated is from the outlier set or if it's a true feature of your data. So next we'll move on to the noisy case. Your data matrix X star is L star plus N star, where N star is an arbitrary noise matrix. And in this case, we achieve an asymptotic recovery of square root R times the Frobenius norm of N star. And the asymptotic error is optimal up to a square root R factor. That is, like, if you did not have any outliers, you would only get asymptotic error of the Frobenius norm of N star, even if you did not have any outliers. So, and we recover the result of the previous case when N star is equals to 0. So how does our work compare to the previous state of the art for the same problem in terms of runtime and recovery error? So we have an almost order n improvement in runtime and square root n improvement in recovery error. And we nearly match the runtime of vanilla PCA. But can we do better than this recovery error in certain situations? So now we consider the case where the noise matrix is random. So in this scenario, N star, each entry of N star is distributed independently according to a Gaussian with mean 0 and variance sigma square. And now we achieve an asymptotic recovery bound of square root R log D times the spectral norm of N star, whereas earlier we were only achieving recovery in the Frobenius norm of N star. And we also generalize the result by Lai, Rao, and Vempala, where they try to robustly recover the mean of a Gaussian. So, like, this is how we compare to previous work. So in terms of recovery error, we have an almost square root ND improvement over the previous state-of-the-art result by Xu et al. We also achieve an improvement of square root D over our own algorithm TORP. But the algorithm that we use to do this is computationally inefficient. We have like an extra n factor in the computation, and we also require n to be greater than d squared. So we need at least d square samples if we want to obtain this recovery guarantee. So now we'll discuss an application of our algorithm to anomaly detection. So you're given a set of URLs like maybe Google, Facebook, Microsoft. And like this set might also contain URLs which belong to websites which maybe they belong to phishing attacks or something of the sort. And you want to separate the good ones from the bad ones. And the hypothesis is that the good websites belong to a low-dimensional subspace. So we compare our algorithm to PCA. And like as you can see, we achieve like a 3% improvement in performance here and a 5% here. And these are like pretty high dimensional data sets, so previous state-of-the-art algorithms are not going to run on these. And yeah, to conclude, like there's been a flurry of recent work in robust estimation. We study a simple outlier robust PCA problem, and we propose an algorithm which is simple, it's fast, and it also has strong recovery guarantees. And an open problem is whether we can get better recovery guarantees when N star is random. And also we have a poster in the evening, so if you have any questions, come over. Yeah, thank you.
So, any questions for Yeshwanth?
You need to know in advance the fraction of how many levels, how many data is bad. In the beginning you show like one part is good and one part is bad, and there was this scalar parameter. Do you need to know in advance?
So the algorithm takes it as a parameter, but in our experiments we use cross-validation with, yeah.
Any more questions? Okay, so let's thank all the speakers for the session again.